I think everything that will be taught till next weekend, till Friday's class. Okay, that will be part of the part of the
Okay.
syllabus for your tutorial.
And ma'am, just one clarification, will it be R based or like previous?
No,
Uh,
no, there are no more assignment-based tutorials. So it'll just be a theory-based test like how you had for your, I think, second periodical test.
okay, ma'am, and just one more thing, I had some doubt regarding second periodical. Can I mail you today?
Yes.
Okay, thank you, ma'am.
Right. I think in the previous class, Kamaya sir took your class, so you'll be discussing, I think, the efficient market hypothesis. Has that been completed?
Ma'am, we started with it. I can let you know where we stopped.
No, that's okay because sir will be taking your class tomorrow, so he'll be continuing with that, I think, tomorrow. All right. So today I'll be teaching you something else. So I hope don't think of it as a disconnect. I'll try and keep it compact so that we complete at least one significant portion today so that we are not leaving something incomplete today. Okay, so and I'll be taking class for only 1.5 hours today since I have another meeting after this. So I'll be taking your class till only about 3:55. All right. So I'll compensate for that half hour on some other day. All right. So let me begin the class. So this is related to WAR models. We've already completed the discussion of WAR models. So some related topics which usually come up in connection with WAR models are co-integration and error correction models. Okay, so you'll see exactly from the structure of the models how they are related. But to explain co-integration in very simple words, if you take two non-stationary variables, okay, and then regress them on each other, sometimes this regression can produce meaningful results if the two variables actually share a meaningful equilibrium relationship. All right. So if there's some sort of an equilibrium relationship between these two non-stationary variables, then you can regress them and use them in the non-stationary form itself. Okay, and estimate a regression model, and the estimates from that model will tell you how these variables are actually moving together, how they adjust in cases of disequilibrium and so on. Okay, so this is what co-integration and error correction models are all about, how that disequilibrium is corrected from one period to the next. Okay, so can anyone quickly tell me, if two variables do not share an equilibrium relationship, then what is that regression called? I've discussed it earlier, so I hope you all will be able to recall. If two variables are non-stationary and I still carry out a regression, that regression,
It's spurious.
yes, okay, yeah, so it's called a spurious regression. We even did some practical work related to that. Okay, so we found that the errors from such models will exhibit certain properties which show that the model is not fine. Okay, and although the regression results seem to be meaningful, actually these two variables are completely independent of each other. There's no relationship between them at all. Okay, that's why the regression is called spurious. So in the case of co-integration and error correction, these are two non-stationary variables where we are allowed to carry out the regression because of the fact that they share this equilibrium relationship. So whatever regression estimates you get, they will be meaningful and they will have some theoretical backing to them. Right? So this is what is given here. Okay, it is possible that a linear combination of integrated variables.
Ma'am, one question.
Yes.
Uh, in spurious regression, the problem is that the two variables are not related or they are not stationary.
There are two problems there. One is that both variables are non-stationary. Okay? Usually we make sure that our variables are in the stationary form and then we carry out the regression. But in this case, both variables are non-stationary, and the only situation where you're allowed to carry out such a regression is if they are co-integrated, if they share some sort of an equilibrium relationship. But in this case, if you have two variables which have evolved independently of each other, there's no relationship between them at all. But when you carry out a regression with them in their non-stationary form, you get some results which look meaningful. Your coefficients are statistically significant and so on. So your results look meaningful. But when you check the errors from your model, you'll find that the error is probably non-stationary. It might exhibit serial correlation and so on. Okay, most of the time the error will be non-stationary. So that is the problem here. Whereas in
Okay.
co-integration models, like I've said here, there is a linear combination of these integrated variables. There's a linear combination of these non-stationary variables where when you carry out the regression, you'll find that the error from your model is actually stationary. Okay, so that's why we are allowed to carry out the regression. So I hope that was clear to you all.
Yes, ma'am.
Okay. So sometimes it is possible that a linear combination of integrated variables, here we mean variables which are not I0, they are I1, they could be I2 and so on. Okay, so we need to difference these variables in order to make them stationary. So these integrated variables, a linear combination of these variables could be stationary. So if you carry out a regression with these I1 variables, then the error from your regression model will be stationary. So this is the relationship which is called co-integration. And such variables are said to be co-integrated. They seem to evolve together. So basically their dynamic paths, when they are evolving in this equilibrium relationship, they sort of seem to move together, or at least their trend paths will be connected in some sense. Okay, so let's look first at a very simple model of money demand. Okay, so in logarithmic form, we can specify this model this way, okay, that the demand for money depends on the price level, then real GDP or real income, and the interest rate. Okay, can anyone tell me what you would expect for the signs of these coefficients, values and signs?
Beta 1 should be positive.
Okay, yes,
Beta 2 should be positive.
okay, and
Beta 3 should be. I'm a little confused. Just give me a minute.
okay, this is the real interest rate or the interest rate itself. Okay,
It would be negative for beta 3.
yes, that's correct. Okay, so beta 3 would be negative. So can you explain why you said beta 1 will be positive and beta 2 is positive? And the person who said beta 3 can explain beta 3.
Ma'am, this is demand for money. So as the price levels go up, you would want to have more money in hand.
Okay, to carry out your transactions.
Yes.
Okay.
Second is it's the coefficient for real income.
Hmm.
So as your real income increases, you would like you have the ability to have more money in hand. So which is why people usually exercise it.
Okay, and your transactions spending also generally
Increases.
increases with a
Yeah.
higher level of income.
And
Yep.
Rahul, you can complete with the third point if you want.
So, ma'am,
Beta.
for the interest rate, if the interest rates are going up, so the cost of holding money is more compared to if you invest it somewhere else. So
Correct.
that is where there exists a negative relationship.
Yeah. Okay, so the interest rate, that's correct. Interest rate is the opportunity cost of holding money. So that's why the opportunity cost increases whenever the interest rate increases. Okay, so you would prefer to invest in other assets rather than hold money. So that's why beta 3 is expected to be negative. Okay, so these are the signs of the coefficients that we're expecting. Okay, now all variables but the interest rate are expressed in logarithms. Okay, now first, okay, how we estimate this model is that first we assume that the money market is in equilibrium, okay, and then we go ahead and start collecting data and so on. Okay, so now because we don't really have data or some variable which captures money demand directly, what we do is instead of money demand, we use money supply, okay, whose information is readily available to us through the central bank. So if the money market is in equilibrium, obviously money demand will be equal to money supply. And so we use money supply as a proxy in some sense to actually estimate our model. Okay. So this is what we do. We use money supply as a proxy for money demand, and then we go ahead and estimate our model. Now, generally in this sort of a model, if you look at the structure of the model and the sort of variables you've used, all these variables are generally non-stationary. They are I1 variables. Okay. So those of you who have used some of these variables for your assignment, you might recall from your own experience that you found these variables were I1. Okay. And differencing them made them stationary most of the time. Okay. Now, if you look at this equation here, and since we are looking at the money market in equilibrium, okay, so we believe that there exists an equilibrium relationship between these variables. Okay? And the theory expressed in that equation states that there exists a linear combination of these variables that is stationary. Okay? That the money market, temporarily there might be disequilibrium where money demand is not equal to money supply. But in the long run, we expect equilibrium to prevail in this market. Okay, so there's some sort of a long run equilibrium relationship between all these variables, and we expect the money market to be in equilibrium in the long run, even though in the short run there might be some situations of disequilibrium. Okay, so basically we are saying that there exists a linear combination of these variables that is stationary. Okay, so we can rewrite one in terms of the error term this way. Okay. Now, what if this error term was non-stationary? Why am I saying that uh, in the long run there will be equilibrium if this error term is stationary? If it's non-stationary, then what does it imply? Can anyone tell me that?
Ma'am, it depends non-stationary in terms of the mean, the variance, or in terms of the covariance. In each,
Uh,
in each of them, it'll have a different takeaway for us.
okay. Uh, Fine. Then let's just say in every sense it is non-stationary. Okay, or it violates the conditions of weak stationarity.
So, ma'am, the first thing we can say is that our model is not good enough because there is a scope of for improvement. When we say
Mm,
something is okay, I'm sorry, I might be wrong.
no, no, no. Neil, I want you to think of what we've just discussed today in the context of today's class and then try to answer the question. Okay, so basically look at equation 1 here. If the money market is in equilibrium, then all these variables, a linear combination of these variables will be stationary. You're expecting that there will be no disequilibrium, and this should be equal to what is coming on the right hand side. Okay, so that your error term basically has a mean of 0 if it is stationary, right? If it's a white noise error term, then it will have a mean of 0. So what am I trying to say here when I'm saying that this error term has to be stationary? So what does it imply about the equilibrium relationship? That what does it mean if this error term is not stationary?
Maybe it's a spurious regression that we're running.
Okay, other than that,
Not sure, ma'am.
think about what we discussed when we were discussing trends and things like stochastic trends. What is the problem over there? Any non-stationary variable, you'll notice that they have stochastic trends, right? And what were the properties of the error terms which were coming in such variables? If you try and recall what you've learned in earlier portions, I'm saying that if you solve, uh, you find the solution to a difference equation for a non-stationary variable, for example, a variable which follows a random walk. Once you get the solution for that variable, you'll notice that it has a stochastic trend. So what does that stochastic trend basically tell us? That deviations from the I'm hoping that one of you will complete my sentence.
Won't converge.
Yeah, deviations from the mean or the long run equilibrium value will basically be permanent. Okay, they will not be temporary. Instead, if this error term is stationary, okay, or if you have deterministic trends, then your deviation from equilibrium is only temporary. Okay, so there will be convergence in the long run, or you will return to the equilibrium path in the long run. Okay, temporarily in the short run, there might be deviations from this equilibrium, but in the long run, you will return to the equilibrium path. So here, if this error term is stationary, if a linear combination of these variables is stationary, it means that basically the deviations again from the equilibrium path are temporary in nature. They are not permanent deviations. Okay? I hope you could recall that portion now, okay? Those who were trying to answer. Okay, since this error term must be stationary, it follows that the linear combination of the integrated variables given by the right hand side of 2 must also be stationary. Okay, so if your left hand side is stationary, obviously your right hand side will also be stationary. Okay, so thus the theory necessitates that the time paths of the 4 non-stationary variables, which are your money supply variable here, then price, okay, then real income as well as the interest rate, the time paths of all these variables have to be linked. They have to be evolving together in some fashion. Okay, so all of them, if you try and imagine some lines, okay, all of them will either be rising together or moving more or less together. Okay, one or two of these lines might appear to diverge temporarily, but more or less they will be moving in the same fashion or towards the same long run path. Okay, so this is an important insight. Equilibrium theories that have non-stationary variables require the existence of a combination of variables that is stationary. Okay, so whenever you have a bunch of I1 variables, you can only carry out the regression and conclude that they share an equilibrium relationship if the error from that regression is stationary, which means that a linear combination of these variables is actually stationary. Okay? If you look at the nature of equation 2, you'll understand why I'm saying that. Here, this is a linear combination of all these I1 variables. And since the error from your model is stationary, so that's why we say that the linear combination of these I1 variables is stationary. Okay, so there are several such, if at any point you have any doubts, please feel free to ask. Okay, so there are
Ma'am, these co-integration models typically don't use lags, or you're
they
assuming the
will,
relation to be, same period, right?
yeah, we are assuming that they are in the same time period. Later on, when we are estimating error correction models, there we will use a lag term.
Okay.
But generally they are uh, in time period t itself. In a var model, you could also have this co-integration coming into the picture. So there you could have lags and so on. We'll see
Yeah,
that a
exactly.
little
My
later.
question was, can you, combine the co-integration with VAR model?
Yes,
Yeah,
we
okay.
can. Okay, so there are several such other examples that we can look at from economic theory itself. Okay, one is the permanent income hypothesis. Okay, so this hypothesis basically says that consumption is a function or it is proportional to permanent income. Okay, and since transitory or temporary consumption will basically be stationary, okay, based on the theory, there will not be very large variations in this. The variance will more or less be constant of this transitory consumption. Okay, so because of this, the permanent income hypothesis says that consumption will be proportional to permanent income. Okay, so these are the two I1 variables here. okay, consumption and permanent income. Okay. So this linear combination of these variables, if you shift this term to the left hand side, Ct minus b ypt, that should be stationary. Okay. This is, if you look at this equation, generally this term is found to be stationary. So even empirically it has been found that a linear combination of these two variables is stationary and transitory consumption is actually stationary. Okay, so these two variables are basically co-integrated. Then if you look at exchange rates also, you'll find that there's a hypothesis called the unbiased forward rate hypothesis. Okay, so basically these variables here are the spot exchange rate and the forward rate. Okay, so what this equation is telling us is that the forward rate should be equal to the expected spot rate one period ahead. Okay, or the expectation of the future spot rate, that is one period ahead. Okay, now generally, okay, in any market, if it is efficient, you might have been discussing some of this in the previous class. Okay, we expect that the actual spot rate will be equal to the expected spot rate. Okay, so the difference between these two will be a white noise error term, basically, which will have an expected value of 0 or a mean of 0. So basically this equation tells us that anyone who is there in the exchange rate market, they cannot systematically make profits by participating in such markets. Temporarily, they might be able to beat the market and actually make profits, but most of the time, the expected spot rate will be equal to the actual spot rate, and so they will not be able to systematically exploit or profit from the market. Okay. So this unbiased forward rate hypothesis, if you use these two equations now, okay, combining these two, we can write the third equation, which
Ma'am,
says
here
that
you mean, sorry, here you mean forward rate or future spot rate?
forward rate. You can also use futures. It will be the same theory applies there also.
Because
In this case,
in
it's
practice,
called,
typically the forward rate, which is in the determined in the current market, is directly a function of interest rates or interest rate differentials.
yes, that
The-
that is
Whereas future
another
spot, I
theory.
agree. That is, yeah. Okay.
Yeah, that is another theory. So there are other forms of this theory itself. If you develop this further, then you get the covered, uncovered interest rate parity hypothesis and so on. So we won't be discussing all that because I don't know if everyone studied that, but this is basically the simplest co-integration model that you can find related to exchange rates. But you can also use futures rates here. Uh, Somebody else had a question. Somebody was going to say something. Okay. So here, if you combine these two equations now, okay, then instead of this, we can just shift this term onto the right hand side, okay, and instead of expectation of the future or forward, sorry, future spot rate, we can just put the forward rate in its place, okay, since from equation A, we get the condition that the expected spot rate is equal to the forward rate, one period ahead spot rate. Okay, so we can write this equation this way, and then we can estimate this equation and see if these two variables are co-integrated. So most empirical work has found that these two variables are generally I1, the spot rate, one period ahead spot rate, and the forward rate. Both are I1 variables, they are non-stationary variables, and they share an equilibrium relationship where a linear combination of these two variables is actually stationary. So if you carry out this regression and then check the error term from your model, you will basically find that this error term is stationary. That's why we say the linear combination of these two I1 variables is stationary. Okay. Then you also have this hypothesis or this theory, the long run purchasing power parity theory, okay, where again you're taking the exchange rate and the foreign price level and the domestic price level. Okay, so basically these two, the foreign price level or the price level in the foreign country and the domestic country, they will be related in some sense. Okay, and you cannot systematically again make profits from exchange rates and so on here. So this also forms an equilibrium relationship, and generally this sort of regression is carried out where these two variables are combined into a single variable and then they are regressed on this variable. Okay, and then the error term from that regression turns out to be stationary. So all these are examples where co-integration has been explored and it has been found that a linear combination of non-stationary variables is actually stationary. Okay? So
Ma'am,
this,
can you zoom in a little bit?
is this better?
Yes, ma'am. Thank you.
So all these examples basically illustrate the concept of co-integration as it was introduced in the form by Engel and Granger. Okay, so this is Robert Engel and Clive Granger. You'll be coming across their names again. Okay, have you all come across any of these names before this? I think one name you have come across, right?
Yes, ma'am.
Okay, which one is that?
Uh, Angle Ranger, they had the co-integration test.
Other than that,
Johansson.
how do you know all this name?
Ma'am, we had mentioned our teacher had mentioned this in our second semester.
Okay, fine. No, but in
We did not get into the theory of it, but
okay,
we had to apply it in some places.
without learning the theory, is it?
Yes, ma'am, without learning theory.
Okay. No, but have you come across any of these names in this semester when you're learning financial econometrics?
I think you mentioned before, ma'am.
In relation to VAR
Granger
model?
casualty.
Yes. Okay. So your Granger causality test, this is the same person here. Okay. So this concept of co-integration was introduced by Engel and Granger in 1987, and they came up with this test, a very systematic method, step-by-step method to actually detect if two variables are co-integrated. Okay. So just consider a set of economic variables. First, we'll cover a little bit of the theory and then we'll discuss their test. Okay. So consider a set of economic variables in long run equilibrium when all these variables, okay, share this sort of a relationship where if you multiply each of these variables by a certain coefficient, okay, these variables, basically the sum of these variables or a linear combination of these variables will be equal to 0. Okay, so this shows the long run relationship between all these variables. Okay, now let beta, okay, and xt denote the vectors where beta has all those beta coefficients from this equation and xt has your n variables. Okay, all of them are denoted by x1, x2 and so on. So there are n such x variables and we are denoting two vectors beta and xt. Okay, we are designating these vectors by these names beta and xt. Now the system is in long run equilibrium when beta xt is equal to 0. Okay, so basically we are saying that when these variables there are no longer any deviations in the paths of these variables. Okay, instead they are moving in a harmonious fashion towards some equilibrium relationship, then we say that these variables are in long run equilibrium when beta xt is equal to 0. Now the deviation from long run equilibrium called the equilibrium error is denoted this way by ET. Okay, so ET is equal to beta xt. Okay, we are just, instead of putting 0 here, we are just putting ET over here to denote that the deviation from long run equilibrium is called the equilibrium error. So this is the relationship which you will see in the long run, but in the short run there could be some deviation which we are denoting by this. Okay, but the expectation of these Et is equal to 0. Okay? Just keep that in mind. Now, if the equilibrium is meaningful, it must be the case that the equilibrium error is stationary. Okay? So for these variables to actually share this equilibrium relationship, like I mentioned earlier, this error term should be stationary, which means that it should have a mean value of 0, the variance should be constant and finite, and the covariance should only depend on the difference in time, not on the location in time. Okay. So here, this equilibrium error has to be stationary. Okay, so the deviations from equilibrium should not be permanent. Instead, they should only be temporary, and this term should be stationary. Now, beta is known as the cointegrating vector. Okay, so the vector of all these parameters or coefficients, which will tell you what is the linear combination that leads to this equilibrium situation. Okay, that vector is called the cointegrating vector. Now, in the money demand case, okay, this vector for the vector xt is given by this. Okay, so you have all your variables here. What is the one for?
The
I
intercept
think for
V naught.
the intercept term.
Yeah, the intercept, correct. Okay, so instead of the intercept, we are just putting 1. Okay, since the variable, if there's a variable x1t, let's say, okay, or x2t, it'll basically be assuming a value of 1 for all time. Okay, so that's why we just put 1 to simplify the notation. This symbol indicates transpose. Okay, so I hope you'll have been able to follow that. So this vector will consist of all these variables in our model, in our econometric model, and the co-integrating vector will be given by this. Okay, so 1 is the coefficient or parameter attached to your dependent variable. Then you have beta naught. Since you're shifting all these variables, you'll be shifting them onto the left hand side, right? So that you get only your error term on the right hand side. That's why you have these negative signs. So you'll have mt minus beta naught minus beta 1 pt and so on. Okay, so these are all the coefficients attached to these variables. Okay, so this is the co-integrating vector. Now the deviation from long run money market equilibrium is ET. And since ET is stationary, this deviation will be temporary. Okay? So this aspect is very important here, that deviations from equilibrium have to be temporary in nature. Now, since we are discussing co-integration in the sense that Engel and Granger were talking about it, we have to note down certain important points here. Okay? So generally, in this sense that we're talking about, it only refers to a linear combination of non-stationary variables. Okay? So we are only talking about linear combinations, not non-linear combinations. Okay? Later on, once you do a lot more work, you might find that there's non-linear co-integration. We are not getting into any of those things right now. Okay? Then again, from Engel and Granger's definition, the original definition, you'll find that co-integration refers to variables that are integrated of the same order. So in our money demand example, all these variables have to be integrated of the same order. All of them have to be I1 variables. You cannot have one variable being an I2 variable and another variable being an I1 variable. Okay? There is another situation called multi-co-integration where you can have a bunch of I2 variables and a bunch of I1 variables and they can still be co-integrated, but we are not getting into that now. Okay. So we are keeping it very simple. We are discussing a very basic model where all the variables are integrated of the same order. Then if xt has n non-stationary components, this is our vector xt, all right? There may be as many as n minus 1 linearly independent, linearly independent co-integrating vectors. Okay, so clearly, if xt contains only two variables, there can be at most one independent co-integrating vector. Okay, so whenever you have n variables in your model, okay, and all of them are, let's say, I1, they share an equilibrium relationship, you can expect that there will be at least n minus 1 co-integrating vectors in your model. Okay? Then the number of co-integrating vectors is called the co-integrating rank of xt. Okay, so the number of these vectors, you might hear this being referred to a little later on. Okay, so the co-integrating rank of xt is nothing but how many co-integrating vectors there are in your model. Okay, and what are these co-integrating vectors? They are basically showing you what are the coefficients that can be attached to these non-stationary variables to create a linear combination of these variables that will be stationary. Okay, I hope this is clear to everyone. Okay. So, for example, suppose if the monetary authorities follow a certain monetary rule, okay, a feedback rule, where they decrease the money supply whenever nominal GDP is high and they increase the money supply whenever nominal GDP is low. Okay, so they're basically responding to the level of nominal GDP. To prevent overheating, whenever GDP is high, they will decrease the money supply, or to stimulate the economy, whenever GDP is low, they will increase the money supply. So this may be represented by this sort of an equation. So we can also write another equation to explain money supply itself, okay, where you can clearly see here that this equation relates to the monetary authorities and their behavior. Okay, so whenever GDP is high, they are going to decrease the money supply. When GDP is low, they will increase the money supply. Then again, related to inflation, when inflation is high, they will decrease the money supply. When inflation is low, maybe we are close to a situation of deflation or something like that, then they might increase the money supply. Okay, so this equation pertains to the behavior of the monetary authorities or how they make their decisions. So here you will find that there's another equilibrium relationship that we are seeing here. Okay, all these variables again will be I1. You will have MT, YT and PT being I1 variables. Okay, and again a linear combination of these variables is going to be stationary since all these variables share an equilibrium relationship. We are again talking about equilibrium in the money market itself. Okay. So given the money demand function in one, now there are two co-integrating vectors for money supply, price level, real income and the interest rate. So the first co-integrating vector we already discussed. Okay, now what is the second co-integrating vector? If you shift all these variables to the right hand side and then leave only E1t on the, shift them to the left hand side, leave only E1t on the right hand side. Then you will be able to write the form of the co-integrating vector. Even without it, you can do it, but you might find it easier. So basically the coefficient attached to MT will be 1 here. Then you have your intercept term, the coefficient attached to GDP, then the price level. Okay. And since there's no interest rate term here, the parameter will be 0 here for the interest rate. Okay. So here we've got two co-integrating vectors, okay, which capture a linear combination or represent a linear combination of these non-stationary variables, which will be stationary. Okay, so the two linear combinations given by beta xt are stationary. Therefore, the co-integrating rank of xt is here 2. Okay, since there are two co-integrating vectors, that's why we're saying that the co-integrating rank is 2. If there was only one co-integrating vector, then we would say that the co-integrating rank is 1. Now, most of the co-integration literature focuses on the case where the variables are I1. Okay, we do not generally discuss situations where variables are I2, I3 and so on. And most of the time you'll find that in economics, it's very rare to come across variables that are actually I2. Okay, and higher orders of integration are even rarer. Any questions or doubts so far? Okay, nobody seems to have any questions. So we'll move on. Now, since I was saying this earlier, the dynamic paths of these variables will generally be linked or connected. Okay, so when they are evolving over time, you'll find that they do not generally stray very far from each other. There might be temporary deviations from each other's paths. You can more or less, if you're trying to imagine two time series evolving, which share a co-integrating relationship, just think that they are moving in some sort of a parallel fashion where temporarily uh, there are deviations where they're no longer following a parallel path. Okay, but eventually they do come back to this same parallel path and they are moving in tandem. Okay, so this sort of observation was made by Stock and Watson in 1998. So they found that co-integrated variables share common stochastic trends. The parameters of the co-integrating vector must be such that they remove the trend from the linear combination. Okay, so remember that stochastic trends are the reason that non-stationary variables are non-stationary, because if you have a stochastic trend, it will mean that the deviation will be permanent. Okay, so once you purge or remove the trend from a linear combination of these variables, then these variables will be able to move together. Okay, or they will share an equilibrium relationship. So here we're discussing a particular example here to help us understand this. Okay, if you think of three time series here, yt, zt and wt. Now each is non-stationary, it's an I1 process, and each has a stochastic trend component given by mu it, and it has an error term epsilon it, which is an independently distributed white noise process. Okay, so all these three variables are evolving in a similar fashion. They have a stochastic trend and there's a white noise error process here. Okay, now if you look at the specific form which each of these variables is taken, okay, if you look at yt, zt, and when you come to wt, okay, here what you will find is that mu wt is nothing but a summation of the stochastic trends that is there in yt and zt. Okay, so mu wt is equal to mu yt plus mu zt. Okay, so when we write the linear combination, okay, we can do it this way: yt plus zt minus wt will be stationary. Okay, because if you subtract wt from yt plus zt, you will be eliminating that stochastic trend. Okay, since mu wt is equal to this, you will be removing the stochastic trend, and these two variables, these three variables, a linear combination of these variables will be stationary, since it will be made up of only the white noise error terms. If you all have any doubts or questions, please stop and ask me. Okay.
Excuse me, ma'am.
Yes.
Ma'am, the thing that we have just done regarding the linear combination, I didn't get this. Like, what are we trying to achieve by doing this?
Okay, so here we are discussing the fact that whenever you have co-integrated variables, they have common stochastic trends. Okay, so they all of them will have a stochastic trend, and you might find that one of them, if you have three variables in our case, one of them has a stochastic trend which uh, is a combination of the trends in the other two variables. So what we're trying to show is, once you are able to create a linear combination, the linear combination should be such that it's able to remove these stochastic trends so that there is no longer any deviation from equilibrium. Okay, so that whatever equilibrium relationship is captured by a linear combination of these variables, it will definitely be stationary now. Okay, because the stochastic trend has been removed.
Okay, ma'am. So the equation that you wrote below, like yt plus zt, this is a hypothetical situation. Like, we have
Yes.
to create one such kind. It mandatory not like this.
See, the thing is, you won't, unless you are trying to do simulation exercises where you're creating a time series and doing it, you will not be doing any of these things on your own. You will be working with data that is already there. So there, when you find a co-integrating vector, Okay, the vector or the parameters of the vector will be such that they are removing the stochastic trend. When you look at the results from your regression, it's not going to tell you anywhere that you have removed the stochastic trend. Okay, but since you're a student of econometrics, you need to understand that that is what you have done when you found the co-integrating vector and created this linear combination. It's just for your own understanding.
Yes, ma'am. Thank you.
So this is what happens. Okay, once you've created this linear combination, you will find that it will be stationary. Okay, so this is our vector xt here. It's made up of these three I1 variables, and it has the co-integrating vector here 1, 1, and -1. If you look at the parameters here, nothing's written, so that's why you'll understand that will be 1, 1, and -1. Okay, this is a purely hypothetical example. Generally, you will find that there will be some other values for the co-integrating vector. 1 or 2 might be 1 there, but generally they'll have some values. So you'll find that co-integration will generally occur whenever the trend in one variable can be expressed as a linear combination of trends in other variables. Okay, so that's why, or that is how you're able to remove the stochastic trend when you create the linear combination, because one variable will have its trend component as an expression of the trends in the other variables. Okay, so it will always be possible for you to find a vector, a co-integrating vector beta, such that the linear combination does not contain a trend. Okay, it's able to remove the trend from this linear combination. Okay, similarly, if you have n variables, so far we discussed 3 variables. Instead of that, if you have n variables, okay, so xt is basically your vector which has your n variables, nx variables. Then mu t is the vector of stochastic trends. Okay? And et is an n into 1 vector which has your stationary white noise error terms. Now, if one trend can be expressed as a linear combination of the other trends in the system, it means that there exists a vector beta such that you'll find that this linear combination will be equal to 0. Here again, you're looking at the long run relationship. Okay? That there will be no deviations from long run equilibrium. Only in the short run you might have deviations from equilibrium, but in the long run the system of these equations or these variables will be in equilibrium. So if you pre-multiply equation 4 with beta, okay, then this is what you get. Now since this term is equal to 0, which we get from equation 5, okay, you'll get beta xt is equal to beta et. And since this is stationary, okay, this will also be stationary. Okay, so a linear combination of these non-stationary variables will be stationary. Okay, this is basically proof of that. Now, when we want to test for co-integration, the simplest method that is generally available to us is the Engel and Granger method. So you all can do this at any time very easily. It's just a matter of carrying out a simple regression and then extracting the error from that regression, testing it to see whether it is stationary or not. Okay, that's just the simple mechanics of it. So we've taken one specific example here. Consider two I1 variables, yt and zt. Okay. Now we want to see whether these two variables are co-integrated, or in other words, whether there's some sort of an equilibrium relationship between these two variables. Okay, so the Engel and Granger in 1987 proposed a very systematic procedure to determine if these two I1 variables are co-integrated of order 1 and 1. Okay, when we are writing the notation this way, this term, you can note it down somewhere. I haven't mentioned this in the notes. I'm just explaining it to you. When we use this notation, the first term here, it just tells us what is the order of integration of the variables. Are they I1, are they I2, are they I0? Okay. Whenever you're talking about co-integration, generally they will not be I0. They will be non-stationary variables, and in most cases, commonly what you will find is that they will be I1 variables. Okay. Then the second term here in brackets, it talks about how many co-integrating vectors are there. Basically, is there one co-integrating vector? Are there two co-integrating vectors, and so on. So this will tell you the number of co-integrating vectors. In this case, since there are only two variables, remember that there will be at the most at least n minus 1, which means at the most there will be at least one co-integrating vector. There could be two also, but there will be a minimum of one at least. N minus 1 has to be there. So here, in this case, the Engel-Granger method helps us to find only one co-integrating vector. Okay, we cannot find all the possible co-integrating vectors. We can only find one. So that's why their procedure helps us to determine if two I1 variables are co-integrated of order 1, 1. Okay, here. So to carry out this test, what we need to do is first determine what is the order of integration of the variables. Okay, determine whether they are I1 or I2 using unit root tests. Okay, now co-integration in their sense, in the sense that they were talking about, requires that all the variables should be integrated of the same order. Okay, so all the variables have to be I1. Okay, just to carry out this simple co-integration test. Then if the variables are I1, only then you proceed. Okay, if they are I0, then there's no point in testing for co-integration at all. It means the variables are stationary. But if they are I1, then you can go ahead and estimate. If they are I2 also, then you come across certain problems when you are using the Engel-Granger test. So generally we don't proceed even in that case. Okay, so your variables have to be I1 for the Engel-Granger method. Now if the variables are I1, then estimate the long run equilibrium relationship in this form. Okay, yt is equal to beta naught plus beta 1 zt plus et. Okay, so you're carrying out a very basic regression. Now, some of you might have the question here that how do you determine which is the dependent variable, which is the independent variable? Okay, so Engel and Granger's test is such that you can place either variable on the left hand side. So either variable can be your dependent variable and you can estimate the equilibrium relationship. Okay, so even if you put zt here and carry out the regression, it's fine. So here just estimate one long run equilibrium relationship of this form. Okay, here we are interested in these parameters, the values of these parameters, beta naught and beta 1. Okay, now
Ma'am, one query.
yes.
When you do this unit root test, they tell you whether the data is stationary or not, right?
Yes.
But they don't indicate whether it is, I1 or I2.
No, that you will understand. If it is, when you test it for stationarity, if it is not, if you find that it is non-stationary, okay, then difference the variable, then see if it is stationary. So if you're able to bring it to a stationary state after one differencing, it means it is I1. If you
Okay.
need to difference twice, it is I2. So that's how you're going to draw your conclusions there.
Okay.
So here, the null hypothesis, again, this I haven't mentioned in the notes. So please note it down. The null for this is that the variables are not co-integrated. Alternative hypothesis is that they are co-integrated. Okay. So when you are checking this, what you need to check is if beta naught is equal to 0 and beta 1 is equal to 1. Okay. So those are the values that we are expecting over here for these two parameters. Beta naught should be equal to 0. Okay, when you test the statistical significance, this should be 0 and this should be 1. Okay. Now, if the variables are co-integrated, an OLS regression yields a super consistent estimator of the parameters beta naught and beta 1. Okay, so this is what has been found by other econometricians like Stock. Okay, in 1987, he found that the estimates are super consistent generally. which basically mean that they converge faster than in OLS models using stationary variables. So whenever you carry out the regression, basically your estimates are going to converge a lot faster, or your algorithm will basically converge a lot faster compared to if you're using stationary variables. Okay. Now, once you've estimated this equilibrium relationship, what you need to do is extract these residuals, okay, and then test them for stationarity. So the residual series contains the estimated values of the deviations from from the long run equilibrium relationship. And these deviations should be temporary in nature. Remember, they should not be permanent, which means that ET has to be stationary. So if these deviations are stationary, it can be concluded that YT and ZT are co-integrated of order 1, 1, since they are both I1 variables, and there is one co-integrating vector which you can get from this equation. Okay. You'll find that they are co-integrated of order 1, 1. Okay. So you can use the Dickey-Fuller test to check the order of integration of the residuals in the following manner. Okay, so they've just told you, you'll have learned this already, so we need not go into it again. Here they are basically using the Dickey-Fuller test, and this is the null hypothesis, alternative hypothesis. Okay, so if you're able to reject the null, it will mean that your error term is stationary. Okay, and if that happens, then you will know that YT and ZT are co-integrated, or a linear combination of these variables is actually stationary. Okay, otherwise you will have to conclude that they are not co-integrated. Okay, so once you conclude this portion over here, when you're testing the null hypothesis of co-integration or not co-integration, the null here is what I mentioned earlier, that there is no co-integration. Alternative hypothesis is that the variables are co-integrated. Okay, that is for the overall angle grandeur test. Now in general, okay, you're not going to be able to use the Dickey-Fuller tables directly. Okay. Now the reason for this is you're using the estimated residuals and not the actual residuals. Okay, so there are certain problems involved in using the Dickey-Fuller tables directly. So instead there is a table of values which has been provided by Engel and Granger itself. So you'll have to compare with those critical values. Generally, it's available or provided directly in any econometric software. Once you carry out the regression, you'll get the results directly over there. Okay. Otherwise, you can search online. You'll be able to find the table of these critical values. Okay. Now, these critical values, you'll have to check it based on the sample size that you're using and how many variables you've used for analysis. Okay. So the critical values will vary based on that, and then you can draw your conclusions after comparing with the critical values. Okay, so do not use the Dickey-Fuller tables directly. Instead, you will have to use the specific values which are meant for this co-integration test. Okay, now in case you find that your error terms exhibit serial correlation, then instead of the Dickey-Fuller test, you can use the ADF test, okay, which will use lagged differences of these error terms itself. Okay, again, the null and alternative hypothesis will have the same form. If you find the error term is stationary, then you can conclude that the variables are co-integrated. Okay, so you can reject the null of no co-integration and conclude that the two variables are co-integrated. Then after this comes the really interesting part where you're seeing how these variables actually correct in the short run. Okay, how do they adjust in the short run so that these deviations from equilibrium are gradually adjusted and then eliminated. Okay, so this is the part where we estimate something known as an error correction model. Okay, I will be continuing. Usually I give you a break at this point. Today I will be continuing because I'm ending your class at 3:55. All right. So here, next what we need to do is estimate something known as an error correction model. Okay. So if the two variables are co-integrated, the residuals from the equilibrium relationship can be used to estimate the error correction model. Okay, now if yt and zt are co-integrated of order 1, 1, where there's one co-integrating vector, both are I1 variables, then the form of the error correction model will be this way. Okay, here you have one equation for yt and one equation for zt. Okay, you're seeing how yt changes in each period in response to the deviation from equilibrium, basically using these two equations 9 and 10. So now if you look at these two equations, this is where your question will be answered of whether we use lag terms and so on. Okay, so this sort of a model is called a vector error correction model. Okay, so it's very similar to a VAR model, but since you're including these error correction terms here, okay, which is these two coefficients alpha y and alpha z. Okay, so these are called the error correction terms or error correction parameters, or also known as speed of adjustment parameters. Okay, so because of their presence, instead of a VAR, it's called a vector error correction model. So here, if you look at equation 9 and 10, we'll look at 9, okay, 10 has a similar form. So basically here you're looking at how the particular variable changes in response to deviations from equilibrium. So you'll be including an intercept. Then here, this is the linear combination of the variables that is stationary. Okay? But if in the short run there is disequilibrium, that's what you're trying to capture here. Okay? So these two variables, this term will not be equal to 0 basically here. So there will be some discrepancy in these values. Okay, so let's say if yt minus 1 minus beta 1 zt minus 1, if this term is positive, okay, then based on the sign of alpha y, you'll be able to conclude what is happening to delta yt. Okay, we'll come back to this in a moment. But basically, if this term is positive, then yt will have to change in response to that, okay, to eliminate the discrepancy or deviation from equilibrium. Then here you could have several lagged differences of this time series itself, yt, and here you will have lag differences of the other variable in your model, which is zt. Okay, so you can include lags based on some lags length selection criteria like the AIC or SPC archaic information criterion. You can use any of these, all right, to determine the lag length. Now delta zt has a similar form here. Okay, so let's look at this here. We won't be estimating it in this form itself. Okay, remember, we are going to use the model in a slightly different form to actually estimate the vector error correction model. Here beta 1 is the parameter of the co-integrating vector from 6. Okay, so what was equation 6 over here? This. Okay, so this helps us to estimate that equilibrium relationship. So beta is the estimate from this regression. Okay. So beta 1 is the parameter of the co-integrating vector from 6, and epsilon yt and epsilon zt are white noise disturbances. Okay, these are the error terms here in equations 9 and 10. And these may be correlated with each other. Okay. Now, I'm guessing that you'll figure out why they are correlated with each other. Okay, let's see if you can actually figure it out. Then here, alpha 1, alpha 2, all these, alpha 1 and alpha 2 are, of course, the intercept parameters. These are the speed of adjustment parameters. These are the coefficients attached to the lagged variables here, lag difference variables. So all these are basically parameters. Okay, now, instead of estimating the equations directly in this form, in the form of equation 9 and 10, what Engel and Granger proposed was to use the estimated residuals that you found earlier from your long run equilibrium relationship. Okay, from this, you extracted the residuals, right? So here you can use the estimated residuals from this and use et minus 1 hat instead of this term, okay, as a proxy for these variables. You can use et minus 1 hat as a proxy for this expression to overcome certain cross equation restrictions. Okay, so there are certain problems with using these variables directly in the model. So to overcome that problem, we generally use this as a proxy, this error term, which has already been estimated. Okay. Thus, the error correction model can be estimated in this form, where instead of that expression, we are just substituting et minus 1 hat. Okay, then go ahead and carry out the estimation process as usual. Then once you estimate, get the estimates of all these coefficients or parameters, okay, you'll be able to find out what is the speed of adjustment of both these variables. Okay. Now I will come back to this in a moment. Let's just look at this part and then I'll come back to equation 11 and 12. Okay. Now since 11 and 12 have the same variables on the right hand side, okay, so all have the same regressor, so OLS can be used as an efficient technique of estimation of the ECM. This is the same thing that we do in VAR models itself. Also, since all the variables on the right hand side are the same, because of that we are able to use OLS for estimation.
Ma'am, can you explain again how are we correcting error in this model?
See, once you estimate this, okay, once you run this regression, you get an estimate of the error terms, right? Okay, once you've got that, then you use that. Okay, so you'll be able to get et minus 1. Okay, so since here you have yt, okay, delta yt on the right hand side, so for each time period, for example for 2020 you'll be using the error term from 2019. Okay, so you'll get it from that equation which you had run, or regression which you had run earlier, and instead of this term, okay, which basically shows you the equilibrium relationship between these two variables, okay, to show that uh, this deviation is being corrected in this error correction model. Okay, to capture this discrepancy, instead of this expression, we just substitute et minus 1 hat. Okay, if you look at this, I'm not sure if you've already understood this part, so tell me if you've understood. I'm unnecessarily telling you.
Yeah, I got this part.
Okay, yeah. So basically, since if you lag this, you'll get et minus 1 here, right? So that's why we are able to use et minus 1 over here. Now, the reason that we do this is if you directly put these variables in, okay, since here on the right hand side, basically you also have yt minus 1, okay, and these two will become contemporaneous in some sense, okay, zt minus 1 and yt minus 1. There could be some restrictions over there. So because of that, to overcome those restrictions, there are certain problems in estimating these two equations directly. So to overcome those problems, we generally use et minus 1 hat.
Okay, ma'am.
So here, excuse me, the next step is, of course, to assess model adequacy and use diagnostic checks on the residuals from our model. Okay, so once you've run these two regressions, you will have to check these two error terms to see if they are white noise processes. Okay, so you'll have to run the usual tests, check the ACF, PACF, then use the Leung box test to check if there's autocorrelation in the error terms and so on. Okay, so you'll have to do all those diagnostic checks like how we used to do for the ARIMA models, and see if the error terms are approximating white noise errors. Okay. Now, in case you find that your error terms are serially correlated, then what you can do is change the lag length of the variables. Maybe increase the lag length or use different lag lengths for the variables. Okay, in that case, you will not be able to use OLS. Instead, you'll have to use a technique known as seemingly unrelated regressions. Okay, so you'll have to use that technique to run the regression. Now here, okay, this is the part that I wanted to discuss earlier. Alpha y and alpha z. Okay, so these are the coefficients which are attached to these error terms over here. So these are known as the speed of adjustment parameters, okay, or coefficients. Now in equation 10, if alpha z is equal to 0, okay, this means that the change in zt does not respond at all to any deviation from long run equilibrium in t minus 1. Okay, so here in equation they're saying 10, but you can also use 12 here. Okay? So since it's the same coefficient, I'm just going to use equation 12. So here if alpha z is equal to 0, okay, then this whole adjustment portion vanishes. Okay, so there's no adjustment at all which takes place in delta zt in response to any deviation from equilibrium. So the only variable which does the adjusting in that case will be delta yt. Okay, so only yt will do all the adjusting. So yt will change in such a way that the deviation from equilibrium is slowly corrected and finally eliminated. Okay. Instead, if you find that alpha y is equal to 0, then you can apply the same logic that yt is not going to do any of the adjusting. There will be absolutely no change in yt in response to the deviation from equilibrium. It will change, of course, in response to these lag terms and so on, but not in response to the deviation from equilibrium. Only zt will respond to the deviations from equilibrium, and zt will adjust slowly so that the whole system is able to return to a situation of equilibrium finally. Okay. Then there are certain other restrictions here. Let's see. Okay, it's not mentioned, so I'll complete this and then I'll come back to what are the other restrictions. So if alpha z is equal to 0, and if all the alpha 1 I is equal to 0 in 1, okay, then it can be said that delta yt does not Granger cause delta zt. Okay, so here it's not actually equation 1, it is equation 12, I believe. Okay, so if you find that alpha z is equal to 0 and alpha 1 is equal to 0. Okay, so if this is equal to 0 and all these coefficients for all the lags are equal to 0, then the way we conduct the Granger causality test in a VECM, VECM is a vector error correction model. So the way we conduct the test in a VECM is slightly different. So here, instead of using only the past values, we also use this speed of adjustment parameter. Okay. So here, if this as well as these coefficients are equal to 0, okay, then in that case, we'll say that yt does not Granger cause zt. Okay. Or if you look at this equation, okay, if I look at equation 11, if alpha y is equal to 0 as well as here alpha 1 2 I, okay, all these coefficients are equal to 0, then in that case we'll say that zt does not Granger cause yt, or changes in zt do not help us to predict yt better. Okay, that's what Granger causality tests basically. So the form of the Granger causality test is slightly different here, where we also include the speed of adjustment parameters. Okay. So alpha y and or alpha z should be significantly different from 0 if the variables are co-integrated. Okay. So either both could be different from 0, significantly different from 0, or at least one of them has to be different from 0. Okay. If one is 0, the other has to have some value. Now, if both alpha y and alpha z are 0, then there's no error correction representation at all. Okay, so it's no longer a VECM and it simply collapses to a VAR model in first differences. Okay, I'll let you look at the equation again so that you can understand this part. So if both these coefficients are 0, this error correction portion completely disappears. So what you're left with is simply a VAR model, but it's not in levels here. Instead, it is in the first difference form. Okay. So impulse responses and variance decomposition analysis can be used to understand the interactions among the variables. Okay, so just like how in a VAR model we used impulse responses, okay, saw how a shock to one of these error terms affects the time path of yt and zt, how yt and zt respond and behave in response to a shock to these error terms. Just like that, in this model also we can give shocks to these error terms and see how these variables evolve in response to those shocks. So we can use impulse responses as well as variance decomposition analysis. Okay, so for variance decomposition analysis, you'll be forecasting these variables ahead and then analyzing the forecast error variance. How much of the forecast error variance is can be attributed to one variable, how much can be attributed to shocks to the other variable. Okay, so that's what you'll be doing there. So this is all about estimating a VECM as well as the angle grandeur test itself for co-integration, okay, and then estimating the error correction model. Now the other thing that I wanted to draw your attention to uh, here, okay, I'll look at this form of the variable. So now if this is positive, okay, so there's a positive, as in yt minus 1 is basically greater than this whole term here. Okay, so this term is positive. In that case, if you find that alpha y is positive, okay, so that will mean that yt is going to increase, okay, or the change in yt is basically going to be positive, or yt is going to increase in response to the deviation from equilibrium. Okay, so that's how you'll interpret these coefficients. Now if this was negative, okay, and this coefficient itself is positive, then once you multiply it, you'll find that uh, yt is going to here decrease in response to the long run equilibrium error, okay, or the discrepancy from equilibrium. Okay, so based on the sign of the coefficient also you can interpret. For example, if this is uh, positive, okay, if alpha y is positive, then yt is going to increase in response to a deviation from equilibrium. If it is negative, it will be decreasing. Also, if you multiply this, okay, this and this, also you'll be able to understand what is going to happen in general. Okay, so the other thing about this variable, or sorry, this coefficient, is that alpha y, okay, the value has to lie between 0 and 1. Okay, it has to be less than 1. So generally you will find that from one period to the other, some portion of the discrepancy is corrected. Okay, so some part of the deviation from equilibrium will be corrected, and in each period yt will slowly move towards equilibrium. Okay, so it does not happen in one shot. Okay, so it will happen gradually. So in every period, some portion of the discrepancy has to be removed and yt has to gradually move towards equilibrium. The same logic applies to zt. So even alpha z has to lie between 0 and 1. Okay, so uh, again some portion of the discrepancy will be eliminated in each period. 100% of the discrepancy cannot be eliminated in a single period. It has to happen gradually. Okay? If 100% of the discrepancy is eliminated in one shot, it means that basically there's no point of really having a speed of adjustment parameter, because all in every period the discrepancy is getting eliminated, so there's no basically no deviation from equilibrium at all there. Okay? So you can interpret it that way also. So it cannot be, it should not be 0. Okay, at least one of these has to be uh, greater than 0. Okay, And at the same time, you'll find that it cannot be equal to 1 also. So it has to lie between 0 and 1. And the other thing is, if one of these coefficients is positive, let's say both are non-zero, okay, alpha y as well as alpha z are non-zero. If one of these is positive, the other has to be negative. Okay, so to eliminate the discrepancy from equilibrium, if one variable is increasing, the other will have to decrease in response, so that eventually the two variables can move towards equilibrium again. So this is how the adjustment has to take place. Okay, so if one is positive, the other has to be negative. If you have three variables, then it could happen that two are positive and one coefficient is negative. Okay, so you will find this sort of a relationship when you look at the coefficients itself or the speed of adjustment parameters. Any doubts or questions so far?
Ma'am, would you be doing any R based practical on any of this?
Yes, I will be doing it probably next week. I want to
Oh,
complete the theory so that we are not lagging behind. Otherwise, we'll have to do a lot of extra classes to catch up. Okay, so,
sure.
since it's the last month, that's why I'm trying to finish the theory. And then, of course, practicals will be a lot easier and faster for all these topics. Any doubts or questions?
Ma'am, one small, it's more my understanding.
Yes,
You are saying this co-integration you are doing in non-stationary variables.
yes,
Is the intuitive logic like this, that their trends are also, related? Is
yes,
that how we get the non-stationary?
their trends are related. So,
Therefore, we get non-stationary result. Stationary
yes.
result. Okay,
Uh, No, the thing is they are non-stationary because all of them have stochastic trends. That's why they are non-stationary. Now, they are variables which once you are able to create a linear combination. So you are able to multiply these variables with some coefficients, where once you are able to do that, one particular linear combination of these variables will be stationary. So if you are able to find such a linear combination, that combination will also be such that these stochastic trends will be removed from these variables. So that's how they become stationary. And that's why you're able to estimate this co-integrating relationship. So that is the understanding. There is a trend in all these variables which is linked. The dynamics of all these trends are linked. They're evolving in some common fashion. And once you're able to remove the trends from these variables by creating a linear combination of them, then the variables become stationary. That combination will be stationary, not the variable itself. I hope that was clear.
yes, ma'am. Something like a linear transformation of matrices.
Yes. Okay, so next we'll be working with matrix algebra actually. So for that, I'd like you all to just go through this portion so that you all are able to understand this better. Try and revise rank of a matrix and what are characteristic roots or eigenvalues. Okay, so please go through that for the next class. My next class will be next week. All right, so Kamaya sir will be taking your class tomorrow. So he'll continue with efficiency of markets, and I will continue this topic on co-integration tomorrow. We have completed the Engel-Granger test today. Okay, and error correction models. So I'll see you next week. Please attend tomorrow's class with Professor Kamaya. Right? Okay, thank you for your time.
Excuse
I'll
me,
be,
ma'am.
yeah.
Sorry, but ma'am, are we supposed? I mean, this thing will be part of the periodical that we have discussed today.
Yes, everything till next week, whatever you have next week, till Friday's class.
Okay, thank you, ma'am.
Okay, so please start preparing well in advance.
Yes, ma'am.
Okay, thank you for your time. I'll see you next week.
Thank you, ma'am.
Thank you.
Thank
Thank
you,
you.
ma'am.
Thank you, ma'am.